Okay, so now we're going to look at a metatheorem called weak generalization. So this metatheorem says that if a collection of hypotheses gamma proves a first-order formula A, and moreover x does not occur free in any formula in the set gamma, so x doesn't occur free in any of the hypotheses, then we know that gamma proves for all x A. So this means that we can generalize this relative theorem A that we've proven from gamma, so long as none of the hypotheses have x occurring free. So that means either x doesn't occur in the hypothesis or it is bound by the universal quantifier. Okay, so some key things to pay attention to. So note that x can actually be free in A. So this is actually a fairly strong metatheorem, particularly if x is free in A. So if we can prove some well-formed formula from a collection of hypotheses, with the added condition that x doesn't occur free in any of those hypotheses, then we can actually generalize this statement A for any x. So that's what this weak generalization says. It's weak because we have this assumption about the proof of A. And as I mentioned in the previous video, this is a proof by induction on the length of a gamma proof of A, right? Because we would assume that gamma proves A, so we have some gamma proof of A. But in this case, we're going to use our logic 2, which is the predicate logic in which the only rule of inference is modus ponens. And in the previous video, I said that we would use that result, that this logic 2 is equivalent to our logic for weak Leibniz, but what I meant was to prove weak generalization. You're not going to be required to know this proof for our class, but it is proven in the textbook if you're curious and want to see how this result is proved. Okay, but let's look at our example. So recall axiom 3 from predicate logic is this statement here. So generalizing A implies B implies generalizing A implies generalizing B. So if we have this axiom 3 and modus ponens, then we actually get a relative theorem, right? So here's our hypothesis. If for all x A implies B holds, then we can prove for all x A implies for all x B. Okay, so now notice here is our hypothesis, and we have this statement here. So now gamma is simply this one hypothesis, and the formula A that we want to prove is this well-formed formula in predicate logic. And we need to, so we have this assumption, and we also need to check that x does not occur free in any formula in the set gamma. But again, taking gamma to be here, we know x does not occur free here because it's bound by this quantifier here, right? So x is quantified by this universal quantifier, so any x that occurs in A implies B will be bound because it's in the scope of this quantifier here. So weak generalization tells us that we can prove from this assumption that this can be generalized over. So we can add a quantifier over x over this statement here. Okay, so the strength of this particular example may not be that strong, but it gives you an idea about how we can apply weak generalization. Right? Okay, we'll see better examples when we start to do proofs, which will not be very helpful in the video, but this just gives you an illustration with some examples of what this is saying. So I hope that was helpful. We have also a corollary to this weak generalization, which simply talks about the hypothesis gamma here. So if gamma proves A, but moreover x does not occur free in any formula used in the proof of A, then we can generalize. So for example, if there are some well-formed formula gamma in which x occurs free, but we don't use them in the proof of A, then this corollary allows us to still quantify over x, right? Because we can simply drop those hypotheses and still prove A. So that's how we would apply the original metatheorem to conclude this. Another corollary, which seems stronger and maybe more useful, is that if A is an absolute theorem, then we can quantify over any absolute theorem. And this could be could be quite strong, but right, we're not using any hypothesis to prove A here, and so simply applying this meta-theorem allows us to quantify over any absolute theorem. Again, to look at a particular example, if we consider any absolute theorem in Boolean logic, for example, the implication theorem here, this corollary simply allows us to add a quantifier over this well-formed form. Okay, so now we need to be a bit careful because, for example, strong generalization is never correct, where strong generalization tells us that if A is a hypothesis, then we can quantify over any hypothesis. And this is simply not true, and it's easy to see why that would be a problem, right? Because if we know A holds for a particular X, we don't necessarily, if we're just assuming that, we can't necessarily assume that it holds for every X. So in particular, to be able to generalize A, we must have a proof for A. We can't simply say, okay, let's take A and then let's just quantify over it. We need to have a reason that we can quantify over that A or generalize that well-formed formula. If it's proved, then that should hold no matter what X is. But in the case where we're simply taking A to be true, we can't then assume that A is true for every X. So if A is an assumption and not proven, we're not allowed to generalize it. And the reason is that strong generalization, or this generalization, is so wrong. And it's so wrong because to show a formula X is not provable, it is in fact sufficient to show that X can be used to prove strong generalization. So this is something we'll look at in Chapter 8, but essentially, if you were to use strong generalization, then you would essentially have shown that your formula is not provable. So using strong generalization simply means we can't prove that. Okay, so next we'll look at the specialization rule and how to combine that with generalization in your proofs.